Everyone talks about AI like some mystical black box that thinks itself. It's not. It's a line. We'll start with a simple straight line, inject some calculus into it, and by the end of this video, we'll understand the exact math behind every machine learning model ever built, including the ones with trillions of parameters, and we'll get there. Now let's start with a simple linear regression model. Consider a 2D plane of axis x and y. Now consider a straight line in that plane. Let the equation of this line be y equal to mx plus c, a very well-known equation where m represents the slope of the line, which means the angle at which it is inclined to the axis, and c represents the y-intercept of the line. Intercept means the distance between the point of intersection of the line and the origin. This is known as the intercept. So now, what if I ask you to predict the future values of this line? What would you do? You can just extrapolate this line along the same straight line. And the mathematical intuition behind this is you can substitute the new values of x into the equation and get the output values of y, plot them onto the xy planes, and simply extend the line like so. Find the y values, plot them onto the graph, and extrapolate the line. This is what I mean when I ask you to predict the future values of this line. That intuition, that exact thing you did in your mind, is known as the linear regression. This is the exact intuition behind the linear regression model. The only difference between you extending a line manually and the machine predicting the future is that the machine has to find out the values of slope and the intercept on its own instead of you giving the equation directly to the machine learning model. It finds the values of m and c on its own from scratch using the math. Now forget about the abstract x and y. Imagine you sell cool drinks and you have noticed that on hotter days you sell more cool drinks. So you get more sales, obviously. But by how much exactly? Can you predict tomorrow's sales of cool drinks based on the temperature forecast you have got? Now consider this as an example for linear regression model. Let's plot the same graph again. Consider the same planes, x-axis or y-axis and the x-axis. On the x-axis, we'll have temperature, and on the y-axis, we have sales. Let's say you have some historical data of temperature versus sales every day for a year. These are your data points on this plane. The number of sales on that day at that particular temperature of the year. Now you can have some extreme outliers like psychopaths buying cool drinks at 0 degrees or at colder temperatures. So this is your plane with all the data points, temperature versus sales. Now let's slightly modify the line equation. While dealing with linear regression, let's write the equation as y equal to wx plus b, where I'll tell you what each one represents. So in this equation, y represents the output. For every value, you give x as an input, and w is called as weight, and the last b is called as bias. Weight is the slope. It tells you how much sales change as temperature changes, directly related. And b is the bias. It's a y-intercept. It accounts for everything you're not measuring. For example, if there's a holiday on that particular day, you there is a high chance of you getting more cells. But we are not accounting for this. We are just considering the temperature as a variable and predicting our cells. So B accounts for those unknown features. Think about it this way. On even a 0 degree Celsius day, you'll have some cells. No matter what the temperature, you will have some cells on that day. So accounting this, we'll add bias to our equation. And in this equation, weights plus bias together, these are called as parameters. You heard this word previously. Every time someone says GPT-4 is just 175 billion parameters, they mean these parameters, and Claude has above 1 trillion parameters. Currently, your model for predicting the sales of your cold drink sales based on the temperature has two parameters, one weight and one bias. And this exact principle works same with the large language models with 1 trillion or billions of parameters. Large language models like ChatGPT or Claude has multiple number of neurons instead of just one single line through them. So they'll have a large number of parameters instead of this simple model. So your cool drink has a two parameters and Claude's model have more than 1 trillion parameters. Okay, moving forward, here is the actual problem. So in this example, we consider the XY axis as sales versus temperature. We can draw an infinite amount of lines through these exact same data points. All of these are valid lines. All of these are valid lines, but only one of them or close to one actually fits the data well, aligns with the pattern, minimizing the error. Now, finding this straight line equation is called as training. This is the exact training we do for the linear regression model. Training a linear regression model means finding the right values of the weight and the bias such that the line fits the data as closely as possible. But how does a machine know which line is the correct one? Which line exactly fits the data points? It needs to measure how wrong it is in predicting the values. Now that's called as the loss function. We measure how wrong is the model using the loss function. Now let's learn about the loss function. Consider this table. In the first column, let's say it is as sales, and the second column contains the average temperature of that day. So your data consists of daily sales values and the temperature for an year. So it consists of multiple rows. First column telling the sales, second one telling the temperature. Now our model is represented using the equation y equal to wx plus b, where x is the input we are trying to give it and y is the output we want to predict. So we don't know the values of the weight and the bias yet. We need to find that estimate the values of w and b during the training of the model. So in machine learning, we don't just pass every single value of this temperature to the x and try to predict the value of y. So what do we do instead is that since x contains the input and it consists of multiple rows of temperature of that day, we consider a matrix of x with the same number of rows and one column, which consists the temperature of first day, second day, the third day, and so on. We pass this matrix into the equation and multiply with the w to obtain a new value of y. So during the training, we start with random values of w and b and we correct them over the time during the training. So the first time when you pass the matrix of x into the equation, we get some predicted values of y which may not be correct, but we'll modify them based on the loss function's value. So the output values of y after passing the x into the equation is called as y cap. Just like how you represent vectors in math. This is called as y cap. The predicted values based on the initial w and initial weight and bias we have chosen. Those predicted values are called as y cap. Let's call the actual sales we have recorded over the year as y. These are the exact numbers we recorded, and wherein y cap is the predicted value from the initial weights and biases. So now the value of loss function, which tells us the difference between the predicted value and the actual value, so that we can correct the model and adjust the weights and biases. So the value of loss function is the predicted value minus the actual value from the table. This is called as the loss function for that equation. So what we have done so far is first choose some random values for W and B. Then pass the input matrix X to predict the output. The predicted values are stored in y cap. We use something called as loss function to measure how wrong the model is, and the value of that loss function is the difference of predicted value for the temperature and the actual recorded value. This is what we have done so far. Now in case of linear regression, we just don't use the loss function as y cap minus y. This gives out both negative and positive losses. For example, consider this is your x and y axis. These are your data points. This is your estimated straight line through the data points. Now all the data points above this line gives you the positive loss function value, and all the data points below this line gives you the negative loss function value. So if you add them up, they might become equal to 0. So what do we do instead is we use something called as mean squared error, MSE. We do this because we have hundreds of data points, and some of them gives out the positive loss function value and some of them gives out the negative loss function values. If you add them up together, they might become close to 0 and we won't get a perfect model. So we use mean squared error to calculate the loss function. So let me give you the formula for this. So the loss function MSE is defined as the mean of sum of the squares of differences between the predicted value and the actual value, where n represents the total number of entries. This mean squared error also does something unique. It penalizes the large errors. For example, consider an error of $1 or 1 rupee between the sales. If you square it, you will just get the 1. But consider this error of 100 rupees. If you square it, you will get 10,000. So the larger the error, the more the model get punished. So it tries to make far less errors. Now consider this. This loss function is simply just a quadratic equation. So as we know, the shape of the graph for a quadratic equation is of U-shaped. Either it's upside U or inverted U. Just remember this, we'll get into this during the gradient descent. So the graph of a quadratic curve is of U-shaped. So every part of this loss function, we have built this from scratch. The y cap minus y, you know this as just simple loss function, the difference between the predicted value and the actual value. N is the total number of entries, which is used to take the mean of this sum, squared sum. So for every input, you take the predicted value and the actual value, square it, then move to the next one, predicted value and the actual value, square it, and so on, and divide it by total number of entries. This is your loss function. This graph is obtained by considering the loss y cap minus y squared on x-axis and that for every MSE value on the y-axis. You get this curve. And also because we are squaring here, we don't get any negative values during this entire summation process. We get only the positive values, so they add up and the loss function increases if the Difference between the predicted and the actual value is large. This is the loss function of our model with just two parameters, only one weight. If you increase the number of weights to two weights, we'll get a total of three parameters, and the loss function becomes a flat plane surface in a 3D plane. This is a 3D plane, and your loss function may become a curve that looks like so in the 3D plane. So with a model something like a GPT-4 with 175 plus billions of parameters, the loss function graph is much more scary. You can imagine it like a land terrain with mountains and valleys. So that's how exact roughly it looks. For now, let's just work with this U-shaped graph to get our mathematical foundation. Since the goal of loss function is to calculate how wrong the model is, we need to minimize the loss so that it gets the things less wrong or prone to less errors. So our goal is to minimize the loss value as much as possible during the training by finding the right values of weight and the bias. This is where gradient descent comes into the picture. Now back to our curve, quadratic curve U-shaped. Let's consider some point over here. We chose some random values of w and b and got the loss function value of this after substituting w and b into the equation. Since this is the graph of loss function and we are trying to minimize this loss function, we need to find the minimum value of this loss function. So in this graph, the minimum occurs at this point. This is the minimum of this loss function. But how do we tell the model to get to that minimum value? So for that, we use gradient descent. So in gradient descent, what do we do is we first find the slope of this point, loss function value on the curve, using the derivatives. For example, let's consider a simple thing. Consider the equation y equal to ax square plus bx plus c. How do we find the slope of this line? We simply differentiate y with respect to x. Use the chain rule if the function contains any more functions internally. So by differentiating the function y with respect to x, we get 2ax plus b. This is the slope of the function that we have considered over here. So what this slope actually tells is that, let's say the graph of this function is same as u-shaped, but let's say it looks something like this, and you are currently at here for the chosen values of a, b and c. So what the slope does is it will give you an idea of how inclined the point at where you are, the inclination of that point. So based on this line, if you move to the left, you will find the minimum values, since the line is more inclined towards the minimum value. If you move to the right, the function stays stable or increases in its value. Consider this example. You are on a peak point of a hill and you are blindfolded. I ask you to reach to the minimum point of that peak, minimum point of that hill, blindfolded. So what you does is you can feel the slope of the hill under your feet. So by just moving slightly to the left or right, if you feel the steep is a bit too low, then you move towards that point to reach the least point of that hill. So that is exactly the intuition behind finding the slope. You give the function a feel of the slope by moving slightly to the right and slightly to the left. If the value is decreasing, then it goes down to find the minimum value of this loss function. So the slope of a function is its derivative. So if the slope is negative, the curve is going downhill, and if the slope is positive, the curve is going uphill. But we want to minimize the loss function value, so we choose this. Let's get back to our original example, y equal to wx plus b. So the value of that curve is loss function equal to 1 by n into sigma of y cap minus y squared. To find the slope of this loss function, we simply differentiate the loss with respect to dw, and we differentiate the loss function with respect to dB. As the actual value of loss function by substituting the value of y cap is 1 by n into the w x cap plus p minus the actual value of the sales. So we need to differentiate with respect to weight and the bias. We might need to use chain rule while differentiating with respect to weight because it consists another variable x with it. So let's differentiate the loss function with respect to both w and b. So these are the partial derivatives. Derivative of loss function with respect to w is 2 by n into the sum of wx cap plus b minus y into the x cap, where x is the input of this function. We can write this equation as 2 by n into sum of y cap minus y into x cap. So this is a value of loss function when differentiated with respect to w. When we differentiate the loss function with respect to b, we simply get 2 by n into sum of y cap by y. So these are the loss function values. And also the slope and gradient mean the same thing. So this is called as gradient descent. We are trying to minimize the gradient of this to get to the least possible minimum value of the loss function. Let's get on to the actual curve of this function. Consider a point somewhere here. After calculating the derivative of this function, we found out the slope to be negative, which means moving right to the curve, we move downhill, decreasing the loss function value. So if we increase the w, that means, which directly means moving to the right, it will decrease the loss value. If we move to the left, then we move upward and the loss function value will be increased. So what do we do is to increase the value of w so that we move to the right and decrease the loss function value, which minimizes the loss function value and finally reach to the least minimum point of this loss value. So every step, once we find the gradient, we move to the next point, calculate the gradient value and try to minimize the loss function and repeat it to the next point and finally reach the minimum value of the loss function. Now how big are these steps? For example, you just chose a large number and you jump from here to directly here. You miss the minimum value of the loss function. Or for suppose you are here and the value between each jump is this long. You jump here, then here, and then here. Still you miss the loss function value here, minimum loss function value. So what do we do is multiply the gradient with some number called as alpha, which is called as the learning rate. So let me write the equation. So the new value of w is old value minus learning rate into derivative of loss function with respect to w. Similarly, in case of b, new value of b is equal to old value of b minus alpha into d loss by dw. In these equations, alpha alpha is called as the learning rate. If the value is too high, you miss the minimum value of the loss function, and if the value is too low, you won't reach the minimum value of the loss function in the least time. If you hit the right amount of alpha value, then you will reach the least minimum point much earlier in the training process. Learning rate too high, you overshoot. You bounce up the model and model never converges. Learning rate too low, you are technically correct, but practically you will be here till until death and you won't find the minimum value of the loss function. So to find the, we'll dedicate an entire video to this learning rate, finding a good value of the learning rate. We subtracted the gradient multiplied by alpha multiplied by learning rate from the old values because we are going opposite to the gradient, and gradient points down the hill. Since we want to minimize the loss function value, we go down the hill. To control the step size, we use alpha, the learning rate. This is the complete training loop. Now this is the complete training loop with real math. First one, the forward pass, where you compute the predicted values of y cap by passing the input matrix x, which contains all the inputs. Then we compute the loss function, which computes the mean squared error between the predicted value and the actual value. Then comes the backward pass. In forward pass, you predict the values with some chosen random w and b, and in backward pass, you correct those random values of w and b to minimize the loss function. So we compute gradient of loss function with respect to w and gradient of loss function with respect to b using chain rule in the process, which is also called as backpropagation. So we update the weight and bias with the new values in backpropagation using the gradient descent. So we update the values, subtract gradient times learning rate, each parameter. Now repeat this entire process for each epoch. And I didn't explain you about the epoch, right? So the epoch means one full pass through the entire dataset after correcting the parameters. So we pass the same data multiple times after correction. So first we choose random values of w and b and pass the entire dataset. Then we correct the values of w and b and pass the entire dataset again. This is the second epoch. So these are called as epochs, passing the entire dataset through the model after correcting the parameters. So over each epoch, the line slightly shifts towards the correct estimated line we want to estimate between the data points. So it gets a little closer to the data. And even the number of epochs is a crucial number during training. If you have more number of epochs, then you overfit the model. If you have less number of epochs, you'll underfit the model. So I'll tell you the details of overfitting and underfitting in a minute. So epoch means one epoch is one full pass through the entire dataset. So after each epoch, the line gets more corrected towards the data points. And I forgot to mention about the train and test split of data. I'll tell you that now. So let's say we have a huge data set. We split 1/3 of data as test set and 2/3 of it as train set. These numbers might shift, but the best practice is to split 1/3 as a test data and 2/3 for training. So what do we do is we train the model on this train data Then evaluate the model on this test data to calculate the things like accuracy and loss values. This is where the terms overfitting and underfitting comes into picture. Overfitting is when Overfitting is when your model just tries to memorize the data points from the input training data, and instead of learning the underlying patterns, it just remembers the values, and it performs well on training data, like it gives 100% accuracy on training data. But when you test the same model on test data, it performs poorly. So this is because of overfitting. It memorizes the values of data set instead of learning the underlying patterns. Memorizing the data set performs well on trained data and poorly on, this is called as overfitting. And underfitting is when the model is just too simple to learn the underlying patterns. It performs poorly on both train and test set. So you also need to find the exact point between overfitting and underfitting by plotting the graphs between accuracy and error. We'll get to that in the deep learning part of it, where we plot the graphs in Colab and find out which epoch is correct between overfitting and underfitting. So there are many points that influence the model which might lead to overfitting or underfitting. One of them is the epoch count. Too many epochs, your model will be overfit. Too less, your model will be underfitting, where it doesn't learn the underlying patterns. It is just too simple to learn the underlying patterns. So this is what each epoch means, how we split the dataset, overfitting and underfitting. Now let's recap what just happened. You started with a line y equal to wx plus b, just two parameters. You learned training means finding the values of those parameters that minimize the loss function value MSE. You learn that gradient descent does that by calculating the slope of the loss curve, and stepping downhill is controlled by the learning rate. And you learn that the chain rule connects the loss to the parameters through the prediction. So this is the entire recap of this video. You learned that Claude has a trillions of parameters, and you exactly know what every one of it does. In video 3, we go deeper into the math with partial derivatives and all the math we learned today, how it maps to the neural networks. And we learn about more models with linear regression with multiple features, XGBoost, logistic regression, random forest, and other things. And one more thing I forgot to tell you is
element of surprise.